Let's do one more of these examples involving the Lagrange error formula. Using the fourth degree Taylor polynomial centered at c equals 1, we approximated the natural log of 1.1 to be blah, 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 with an error of, it was super small. You can see it right there for yourself. Demonstrate this error using the Lagrange remainder. So what happens on the AP exam if you have to demonstrate this, usually on a free response question, they give you a number to shoot for. They tell you to show that your error is less than, and then it gives you some sort of number. And you're expected to use, of course, the Lagrange remainder formula, which is what we are about to format here. So we used a fourth degree Taylor polynomial, right? So we are bounding our error on the fourth degree, and this was centered at 1.1, or no, it was centered at 1, but we're finding the error at 1.1, and it should be less than or equal to. It is the maximum value of the n plus 1th derivative, so the n plus 1th derivative is going to be the fifth, so it is the fifth derivative at some maximum value, which we're going to call z. Wait a minute, what am I doing? That should be 5, and this should be z. And that z, remember, lives in between 1 and 1.1. And it could be either one of those two things, or, none of the above. That's going to be divided by the fifth factorial, n plus 1, times x minus c. So our x value is 1.1 minus 1 as our c value, raised to the n plus 1th power, so that's to the 5th power. All right, so that's what we got to work out. So I'm going to clean this up in just a minute, but let's first focus on the fifth derivative. I need to probably go back in my work and see what the fourth derivative was, because I think that's about as far as we took our derivatives of this. If memory serves, let's see, where is this guy? Here it is. All right, so our fourth derivative was negative 6x to the negative 4th. You remember that? Why didn't you just shout it out then? Okay, so we've got the fourth derivative. You want to throw an x in there? Okay. Was negative 4x to the, no it wasn't, negative 6x to the negative 4th power. So now let's take the fifth one. Leapfrog 24x to the negative 5, or if you please, 24 over x to the 5th. Remember, we want to find the maximum value on the interval from, let's say, 1 to 1.1, basically, on this thing. So let's try to graph it. Doesn't have to be perfect. So think about this. On this thing, we have an asymptote here at 0. Here, let me throw it in red. Joop, 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 joop. And then you're going to have a part of your function over, well, this should be green, I think. Part of your function is going to be over here, right? And then part of your function is going to be down here. And you can see that in this first quadrant, which is where we're basically centered, this would be the number 1, and this would be the number 1.1. As a decreasing function, the maximum value actually occurs over here at our center point of 1. So that's where we're going to evaluate in order to get our maximum value. We're going to evaluate it at 1. The fourth derivative. No, the fifth derivative. So that looks like this. Fifth derivative evaluated at 1 is going to be a big fat 24 divided by 1 to the 5th power, which here, let me do that calculation for you real quick. I'm going to punch some stuff on the calculator. Okay, it's 24. My phone's screaming at me for doing something really stupid. Okay, anyway, so let's flesh this thing out, shall we? I think I was using this color. I'm going to come back down here. Let's copy and paste this. Or just move it. Yeah, that makes sense. All right, and so I know that this part right here is now 24. We just maximized it. We got 24. I'm going to take out 5 factorial. You guys remember what that is, right? So it's like 24 times 5, which is 120 there. And then when I subtract these, I just get 0.1. But I'm going to write that as 1/10 like this, right? And then actually rewrite that like, and all of these are positive, so I don't need the absolute value anymore. So I've got 24 over 120 times 1 over 10 to the 5th. Or you know what? I'm just going to write that as 10 to the negative 5. It's almost like scientific notation, right? Okay, and now let me simplify this fraction over here. You know, 24, that looks like a factorial in and of itself, right? It's like 2 times 3 times 4. That's 6 times 4 over. And then this 120 was 2 times 3 times 4 times 5. And look at what happens. Cancel, 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 cancel. And we're just left with 1/5. Less than or equal to 1/5 times 10 to the negative 5th power. And then maybe, you know what, maybe I just take that and turn that into 0.2 times 10 to the negative 5th power. And then this tells me to move that decimal place 5 spaces to the left. So I'll just put a whole bunch of zeros in front of this. Do you think this is enough? It's probably enough. Let's put one more just in case. Okay, so my decimal place is right here. I'm going to move that 1, 2, 3, 4, 5 spaces. So there's our number. 0.1, 2, 3, 4, 5. Man, I had to count those. There we go. So we know that our error here is this is fourth, right? Of 1.1. Joop, joop. It's got to be less than or equal to that number. All right, like I said, on the AP exam, they give you a number to shoot for. You're just trying to make sure that your number is less than the one that they give you. And ours was pretty close. This was the one that we got from the calculator. Look, I'm going to count these zeros up as well. 1, 2, 3, 4, 5. All right, and that would round that thing up to a 2. But we got way more accurate because we just threw those things right into our calculator. But you know what? This guy's like, hey, I don't need a calculator. I can get pretty close to that. And it certainly did, right? So 0.00002. Which brings us then to the end of our lesson. Taylor polynomials, what are we using these things for? We're using them to approximate a function that's really hard to work with by hand, but polynomials, they're super easy. So we're going to replace our function with a Taylor polynomial, and hey, we want to know how far off we are with our approximation. Enter the Lagrange remainder, and it's going to tell us based on, think of it as the next term in our Taylor polynomial. We went up to the nth. Let's just carry it one more term, n plus 1th, and just trying to maximize that derivative, and that's basically the Lagrange remainder.